Rotating electrical machinery is a part of much military equipment. Whether it is a simple blower or a complicated electronic device in a missile, they all depend on the proper functioning of rotating electrical equipment. Two types of motors and generators are commonly in use: alternating current or AC and direct current or DC motors and generators. This film will show the principles governing the operation of DC motors and generators. Basic to the understanding of DC motors and generators is the simple generation of an electromotive force, an EMF. Mechanical energy, the moving of a wire or conductor across a magnetic field by hand in this instance, produces electrical energy. The magnetic field is composed of lines of force. As the conductor cuts these lines, an electromotive force, or EMF, is generated in the conductor. Moving the conductor down through the field makes the needle of a voltmeter deflect one way, which means the EMF has one direction. Moving the conductor up through the field produces the opposite deflection of the needle. The EMF has now changed direction. Moving the conductor back and forth with the field does not make the needle of the voltmeter deflect. There is no EMF because the conductor is not cutting the field. To illustrate the direction of current flow, the conventional symbols will be used. Current flowing in a conductor away from us is represented by a cross, toward us by a dot. However, moving a conductor in and out of the field in this straight reciprocal fashion is awkward and impractical. A simple generator of EMF can also be made by rotating a single turn coil within a stationary magnetic field of two magnets with opposite polarity. The loop now, in effect, becomes two conductors because both the top and bottom sections cut magnetic lines during rotation. Since they cut lines of force of opposite directions as they rotate, EMFs of opposite polarity will be generated in the conductors. In order to have current flow in this circuit, polarities of the two conductors must be opposite. The amount of EMF generated at any instant is determined by three factors: the strength of the magnetic field, that is, the number of lines of force, the length of the conductor cutting the lines of force, and the velocity with which the conductor is turning. We can determine the amount of instantaneous EMF by a simple formula. The instantaneous EMF E equals B, the strength of the field, times L, the length of the conductor cutting lines of force, times V, the velocity of the conductor. An increase in the number of lines of force or the strength of the field increases the instantaneous EMF in the conductor. Increases in the length of the conductor cutting lines also increases the EMF. And finally, the greater the velocity of the conductor, the greater the EMF. This formula assumes conductor motion in a straight line. That is to say, cutting the same number of lines for each increment of its motion. But the conductor in an actual machine is not moving in a straight line, but rotating. When the conductor moves in a rotary path, the number of lines cut varies depending on the position of the conductor. At the top of the field, for instance, no lines are being cut and no EMF is generated. As the conductor keeps turning, the number of lines cut increases, so that at a quarter turn or 90 degrees, the maximum number is being cut and maximum EMF is generated. Again, at 180 degrees, no lines are cut, no EMF. We reach a maximum again at 270 degrees, and finally, again at 360 degrees, no lines are cut. The conductor has rotated 360 mechanical degrees, which correspond in this instance to 360 electrical degrees. Therefore, when the conductor moves in a rotary path, another factor is added to the original formula for the determination of instantaneous EMF. The formula that now applies is instantaneous EMF equals field strength times the length of the conductor times velocity multiplied by sine theta. Theta is the angle formed by the flux line and the motion of the conductor. The number of lines cut and the amount of EMF generated is proportional to the sine of the angle formed by the magnetic lines with the conductor motion. A graph of EMF versus conductor position during one revolution will be a sine wave representing alternating current, or AC. All rotary generators produce AC internally. What you have seen so far is really the theory and operation of a basic AC generator, but our purpose was to explain the principles of operation of a DC generator. To get direct current, we will attach each end of the conductor to a segment of copper, forming a commutator. Now our machine is a DC generator. The commutator rotates with the loop. Stationary contacts, carbon brushes, ride on the commutator segments. They provide a means of connecting a meter or any other load to the generator. The loop of a conductor, wound on a rotor, and the commutator are referred to as the armature. As the loop revolves and the EMF in the conductor reverses polarity, the connections to the load are also reversed, and the current flow will maintain the same direction externally. Represented graphically, the output amplitude still varies. The DC is in the form of pulses. It is a pulsating direct current, or PDC. The pulsation from 0 to maximum, twice for each revolution of the loop, is called ripple. This ripple can be reduced by adding more loops and more commutator segments to the existing armature. Two loops at right angles connected to 4 commutator segments provide 2 outputs instead of 1. These outputs are 90 degrees displaced or apart, which combine to smooth the DC output. However, even with 2 loops and 4 commutator segments, the rectified curve is still somewhat irregular. By adding magnets, we increase the number of fields cut by the armature. As we increase the number of loops and commutator segments, the variation between maximum and minimum value decreases. This, in effect, tends to flatten the DC output. Practical DC generator armatures have a great many loops wound on a rotor. The field is composed of many electromagnets. Together, these factors tend to create an almost pure DC output. An important problem in the design of generators is the prevention of sparking between the commutator and the brush assembly. The prevention of sparking depends on the position of the brushes. This line through points of zero generated EMF is called the neutral plane. Placing the brushes in this neutral plane reduces the tendency for sparking between brushes and commutator, because during the time a brush is touching both commutator segments, there is no difference in potential between these segments. Theoretically, no sparking should occur at the commutator brushes when they are placed in this position. But the current flowing in the armature loops or coils sets up a magnetic field of its own. This magnetic field interacts with the main magnetic field and distorts it. The distortion causes a shift in the neutral plane and sparking at the brushes. The effect is called armature reaction. Sparking may cause severe interference in nearby electronic equipment. There are two ways of maintaining the neutral plane in its correct position and thus avoiding sparking. It may be done by the adjustment of the brush position. The brushes are adjusted to lie in the adjusted neutral plane. The other way of maintaining the neutral plane is by adding interpoles to the generator field. These interpoles are small magnets placed between the poles of the main field magnets. The interpole fields oppose the fields created by armature reaction. The neutral plane is moved back toward the correct position. In addition, to further counteract armature reaction, windings called compensating windings are sometimes placed in the main pole faces. The current in these windings is armature current flowing in opposite direction to the current in the armature conductors. Magnetic fields in DC generators may be produced by electromagnets or permanent magnets. Permanent magnets are used in relatively small devices like a field telephone ringing generator. In larger generators, the field is created by electromagnets. The field winding used in this DC generator can be represented by a symbol. The symbol is that of an iron core inductor. Current to excite the field windings can be supplied from an external source. In that case, the generator is classified as separately excited. A small part of the generator's own output can also do the exciting. In that case, it will be a self-excited generator. Self-excited generators must be initially magnetized. The residual magnetism in the core of the field winding provides enough magnetism to begin generator action. The field coil winding may be connected in several ways. This is a series wound generator, which means the field coil is in series with the armature. Because of this series arrangement, it has poor voltage regulation. The reason for this can be demonstrated in the following manner. Additional load will cause more current to flow in the field coil. Increase in field strength increases voltage. Increase in voltage causes more current to flow. This continuing action stops only when the core is saturated. When the load is increased, the voltage will increase. When the load decreases, voltage will decrease. Voltage regulation in the series wound generator, therefore, is very poor. when instead of in series, the field winding is connected in parallel with the armature and the load, we have a shunt wound generator. Now the field current is independent of the load current. Therefore, an increase in armature current will not cause an increase in the voltage output. Voltage regulation here is greatly improved. In shunt wound generators, therefore, changing load causes relatively small change in voltage output. By changing the armature winding, a compound wound generator results, which combines the best features of both types, the series and the shunt wound generator. When windings are arranged so that magnetic fields oppose each other, it becomes in effect a series generator. This is used only where constant current is the prime requirement, such as in arc welding. By changing the magnetic polarity of one of the field windings aid one another. As a result, this compound wound generator has good voltage and fair current regulation. A graphic representation of generator output characteristics with terminal voltage plotted vertically and armature current horizontally would look something like this. As we have seen, in the output of the series wound generator, voltage regulation is very poor. In parallel or shunt wound generators, the voltage regulation is fairly good, but current regulation is poor. Compound wound generators offer a flat compounded output that is normally most desirable. It combines the good features of both the shunt and series wound generators and provides stable voltage output under changing loads. As we have seen in our analysis of the DC generator, its primary function is the conversion of mechanical energy to electrical energy. If we now reverse the procedure and connect an electrical power source to the generator, we have a DC motor instead of a DC generator. Motor action can be illustrated by attaching a power source to a conductor which is inside a magnetic field. The electric current creates polarity in the conductor. The south pole of the magnet attracts the north pole of the conductor and repels the south pole. The north pole of the magnet attracts the south pole of the conductor and repels the north pole. This creates movement, depending on the direction of the steady magnetic field. The movement also depends on the direction of the current flow through the wire. By changing the polarity of the battery, the conductor now moves in the opposite direction. To see what really happens, let's go to a drawing again. Here, a conductor is suspended in a magnetic field. Current flow from a power source creates its own magnetic field in and around the conductor. This field around the conductor reacts with a main magnetic field to cause motion of the conductor either out of the field or into it. The arrow point indicates the direction of the current flow in the conductor. In this case, the flow is toward us. The field of the conductor has the same direction as the main field above the conductor and the opposite direction of the field below the conductor. These two magnetic forces added together distort the lines of the main field upward. The field above the conductor is thus made stronger and the field below the conductor is made weaker. So the conductor moves down. Conversely, when current flows in the opposite direction, that is to say, away from us, the field of the conductor opposes the main field above the conductor. This aids the main field below the conductor, distorting the lines down. The field below the conductor is thus made stronger, while the field above the conductor is made relatively weaker. This forces the conductor to move up. With this basic principle of motor action understood, we can now examine the DC motor. The basic DC motor, like the DC generator, consists of a pair of magnetic poles, an armature made up of a single turn loop, a commutator, and a brush assembly. As we have seen, a conductor in a magnetic field will move when a voltage is applied to it. With the voltage applied and the magnetic field and current flow as shown, the right conductor will be pushed down, while the left one is pushed up. Since the forces on each conductor are now in exact balance, there will be no more motion. Adding another loop and two commutator segments ensures that at no time will balancing forces cancel each other out. With this setup, there will be motion at all times. As one commutator segment is moved away from the brushes, another now takes its place and the movement continues. The greater the number of loops in the armature, the smoother its motion. For this reason, rotors in practical DC motors have many loops. Since current in the rotor loops must reverse each half cycle, two commutator segments per loop are required. Here in the motor, as in the DC generator, there is a neutral plane. The interaction of the conductor fields on the main field causes this neutral plane to shift and sparking to occur when a load is added. Sparking in DC motors also produces burned commutators and interference in nearby electronic equipment. This sparking can be prevented in one of two ways. One is by the adjustment of the brush position. The brushes are moved until they lie in the adjusted neutral plane. In the motor, as in the generator, small interpoles between the poles of the main magnets are also used to eliminate the shift of the neutral plane. These interpole fields tend to oppose the fields created by armature reaction. The neutral plane is moved back toward its correct position. Also aiding are compensating windings, which carry armature current in the opposite direction to the current in the armature conductors. The neutral plane is thus maintained in its proper position. DC motors operate most efficiently when sparking is eliminated. We saw earlier that when a conductor is moved by mechanical energy in a magnetic field, an EMF is generated. This is generator action. In the DC motor, when rotation is desired, it is necessary to apply an EMF to the conductor. However, when used as a motor, an opposing EMF is also generated in the conductor. This is called the counter-electromotive force, or CEMF. By Lenz's law, the generated CEMF must oppose the applied EMF. The amount of CEMF depends on the speed of rotation. This is of practical importance in large motors. When starting large motors, the problem exists of limiting current through the rotor windings until a CEMF can be built up. If the full current is applied before the CEMF develops, it may burn out the rotor windings. Starting boxes are used with DC motors in order to avoid this application of current before the CEMF is built up. Here is a basic shunt motor with its starting box. In the starting position, the circuit to the rotor windings is closed through a series of large resistance coils. As the lever of the switch is moved, rotor speed and CEMF build up gradually, and the resistance coils are subsequently cut out until running speed has been reached. the lever is held in the fully open position by an electromagnet. If for any reason the power should fail or the field coil open, the electromagnet becomes de-energized and the lever is returned to the starting position by spring action. Just as in DC generators, DC motors seldom use permanent magnets for the field. Instead, electromagnets are used. Like with a DC generator, field windings are constructed in several ways. Each type of winding has special characteristics, special values, and specific uses. The series wound motor has good starting torque or turning force. Torque depends on armature current and on field strength. Since field strength is proportional to current, the high starting current before CEMF is developed affects torque as the square of the current. The motor begins to turn, attempting to develop enough CEMF to completely oppose the applied EMF. The load prevents this, acting to control the speed of the motor. But if the load is suddenly removed, like in the case of a broken belt, the motor will build up speed trying to develop more CEMF until it destroys itself. The shunt wound motor has less starting torque, but it is less dependent on load for speed control. In the shunt wound motor, the field coils are connected in parallel directly across the DC input terminals. The starting torque is not as great as in the series motor since field strength is not affected by armature current. The speed of a shunt motor is fairly constant under conditions of changing load. As more load is applied, the speed of the armature decreases. This decreases the CEMF and increases the current input. The increase in current input boosts the coupling between the field and armature and increases the torque, causing the motor to resume approximate running speed. A sudden reduction in load will not damage the motor because the field current is independent of rotor current in the shunt wound motor. The desirable characteristics of both the series and shunt wound motors can be achieved in the compound wound motor. In order to obtain good starting torque, the series field is used. When running speed has been attained, a centrifugal switch cuts out the series field and cuts in the shunt field. It is now a shunt motor and the speed regulation is good. Compounding provides good starting torque and good speed regulation. This allows for efficient operation and minimizes the possibility of damage to the motor. Now for a quick summary. The operation of all rotating electrical machinery is based on one simple principle: the generation of an EMF. The principle is used in the construction of a simple AC generator. The generator output E, or instantaneous EMF, equals B, strength of field, times L, length of the conductor, times V, velocity of the conductor. But because the movement of the conductor in the field is actually circular, we must also multiply with the sine of the angle formed by the lines of force and motion of the conductor in order to arrive at the EMF. All generators are basically alternating current generators and produce AC internally. The basic AC generator becomes a DC generator when a commutator is attached to the conductor. Each commutator segment rotates with its respective conductor, producing a direct current. This current, which is a pulsating current, is made smoother by the addition of more magnets and more loops. Sparking in a generator is sometimes caused by a shift in the neutral plane. This can be corrected by adjusting the brush position. Or by the use of interpoles and compensating windings. Current for field windings may be supplied from an outside source, in which case the generator will be separately excited. Or the current may be a part of the generator's own output, in which event it is called self-excited. Generator field windings are constructed in three ways. Series wound, where the field windings and the armature are in series. Shunt wound, in which the field winding is in parallel with the armature and the load. And compound wound, in which the best features of both the shunt and series wound generators are combined. Voltage regulation in the series wound generator is poor. In the shunt wound generator, voltage regulation is fairly good, but current regulation is poor. Compound wound generators provide stable voltage under changing loads. This output is normally most desirable. Motor action is the opposite of generator procedure. In a DC motor, voltage is applied to two or more loops in a magnetic field. This causes polarity in the loops. The interaction of this polarity with the polarity of the field makes the loops rotate. This is the basic DC motor. When the conductor of the motor is rotated by an applied EMF, it also generates a counter-electromotive force. According to Lenz's law, this generated CEMF must oppose the applied EMF. As in generators, field windings in DC motors are of three types. The series wound motor has good starting torque, but since its only governing factor is the load, the speed regulation is poor. If the load is disengaged suddenly, the motor will race to destruction. In shunt wound motors, with the field coils connected in parallel across the DC input terminals, the starting torque is not too good, but since the field current is independent of the rotor current, the speed regulation is quite good. The compound wound motor combines the best features of both types. It uses a series section for good starting torque. Then it switches to a shunt arrangement for good speed regulation. DC electrical motors and generators are at the heart of much military equipment. A proper understanding of them is therefore important. Alternating current is the most practical and versatile source of power for most electrical and electronic applications. High voltage alternating current can be transmitted over long distances without appreciable loss and readily transformed to low voltages for practical use. AC can also be radiated from an antenna. This capability is responsible for the development of radio communication. All generators produce AC internally. In this basic AC generator, the arms of the loop cut lines of force in opposite directions, causing electromotive force of opposite polarity to be generated in the conductor. To maintain the AC character of the output in this generator, we use slip rings instead of the commutator segments used in the DC generator. This use of slip rings is the only structural difference between AC and DC generators. One complete revolution of the armature will produce one cycle of alternating voltage. If the armature rotates once each second, the frequency of the alternating electromotive force or voltage is 1 cycle per second. 10 mechanical revolutions of the armature per second produce a frequency of 10 cycles per second. Frequency, or the number of cycles per period of time, is directly related to the rotating speed. In this example, the two-pole machine used has one magnetic field. As the armature makes one revolution, one magnetic field is traversed. Adding another pair of poles adds another magnetic field. Now there are two magnetic fields. The armature moves through one field in half a revolution. In one complete revolution of 360 mechanical degrees, the armature passes through two fields equal to 720 electrical degrees, and 2 cycles of AC are generated. Frequency can be changed in the AC generator by the introduction of additional magnetic fields. The relationship between mechanical and electrical degrees depends on the number of poles in the generator field. In a 4-pole field, we saw that 360 mechanical degrees equals 720 electrical degrees, a ratio of 1 to 2. In a 6-pole field, the ratio is 1 to 3, and so forth. The formula for frequency in an AC generator can be expressed as follows. F, which is frequency in cycles per second, equals P, the number of poles, times N, revolutions per minute, over 120. We can find the frequency of a 4-pole AC generator whose speed of rotation is 600 revolutions per minute by substituting 4 for the number of poles, P, and 600, the RPM, for N. Here the frequency is 20 cycles per second. The output of the AC generator may be increased by the addition of loops to the armature. Changing the construction of the armature in this way provides additional outputs. The resultant output here is the algebraic sum of the individual waves. The armature of the practical AC generator is wound with many turns of wire. There are several different types of AC generators, or as they are sometimes called, alternators. This is an elementary single-phase AC generator. The armature of the single-phase AC generator is wound with many turns of wire. These coils are connected in series, so that at any given instant of time, the total voltage induced is the sum of the voltages induced in each individual coil. The principles used in the construction of a single-phase AC generator are also employed in 2- and 3-phase AC generators. The 3-phase system has 3 loops, set 120 degrees apart, 6 slip rings, and 3 outputs represented by these 3 voltmeters. The output, as shown here, will consist of 3 individual AC voltages, identical in amplitude and 120 electrical degrees out of phase. The 3-phase system has many practical applications and is widely used. Alternating current generators using electromagnetic fields, however, cannot be self-excited. DC is needed to excite the field. In practice, a small DC generator set in tandem with the main machine in one housing does this. Large AC generators are sometimes constructed with a stationary armature and a rotating field. Here, the coils of the armature are set around the circumference of the yoke. The poles of the field rotate within the armature to avoid the use of slip rings and to obtain direct connections to the load. Brushes and slip rings are used, however, to connect the AC generator to the outside low-voltage DC source needed to excite the field. Sparking brushes at low voltage does not represent a serious problem. Because AC has proven itself a versatile and practical type of power, many kinds of AC machinery are in use. To operate as a motor, an EMF must be generated in the conductor. We know that rotating a conductor through a magnetic field generates an EMF. The same effect can be accomplished by holding the conductor stationary and rotating the field instead. Lines of force are still being cut, and so an EMF is generated. Either the conductor or the field must remain stationary or move at a slower rate. That is to say, relative motion must always exist between the armature and the field in order to generate an EMF in the armature. We can construct an AC motor by closing the loop ends of the armature, thereby inducing a larger current in the loop and creating stronger magnetic fields around the conductors. This is a simple induction motor. The interaction between the conductor fields due to relative motion and the rotating magnetic field causes the rotor to move, but at a slower pace than the rotating field. If the speed of the rotor and the field were the same, there would be no induced EMF. No lines of force would be cut and no field built around the conductor. Obviously, there can be no motor action under those conditions. This, however, is an impossible situation. For if the rotor stops while the field continues to turn, relative motion will have been re-established. Lines of force are being cut once more. An EMF is generated and the resultant magnetic field will cause the rotor to move again. So far, we have rotated the field by physical means, which is impractical. It is necessary to find a way to rotate the field electrically. We saw earlier how three voltages 120 degrees out of phase were generated. This voltage can be used to rotate the field electrically. Six magnets set in a circular arrangement represent the field of a three-phase induction motor. These three pairs of conductors, one pair for each AC phase, supply the field. Because of the time difference in the three phases, the poles will be energized in successive order, thus rotating the field electrically. Since the rotating field is cutting the rotor, it will rotate in the same direction as the rotating field, but at a slightly slower speed. Three-phase motors have special value in situations where it is important to maintain constant speeds under changing loads. Another type of AC motor is the two-phase induction motor, used especially where it is necessary to change direction of rotation quickly, such as in a radar antenna. The current used in this motor is two-phase AC. That is to say, two separate AC voltages 90 degrees out of phase. Just as in three-phase motors, the phase difference is used here to energize the field poles progressively, thus causing electrical rotation of the magnetic field. As in all induction motors, electrical rotation of the magnetic field is a primary objective. Again, the rotor turns in the same direction as the magnetic field, but at a slightly slower speed. The two-phase motor in this installation is called on to change its direction rapidly. This rapid change of direction is accomplished simply by reversing the polarity of only one set of poles in the motor. The polarity of the second set of poles will remain unreversed. The field will now rotate in the opposite direction, with the rotor following at a slightly slower speed. The most common type of current available in most sections of the country is single-phase AC. For that reason, single-phase induction motors are widely used for many and varied purposes. In the single-phase induction motor pictured here, the single AC output energizes both sets of poles simultaneously. There is no phase difference in this arrangement, and so the field will not rotate. As the cycle of the AC wave changes, the poles pulsate alternately. But since there is no relative motion, the rotor will not turn. The major problem is getting it started. If the rotor is started by hand, relative motion is created and the motor will continue to run. But this is not a very practical method. There are several ways to start a single-phase induction motor. One method is the use of shaded poles in the field. A shaded pole is attained by placing a copper ring in a slot over half the pole. The copper ring on the shaded half of the pole increases the inductance of that half. That causes the magnetic field of the shaded half of the pole face to lag behind that of the unshaded portion, creating a rotational effect. Lines of force will emerge from this unshaded section of the pole face first. The inductance caused by the ring makes the shaded portion of the pole lag behind. This alternating pulsating action creates a phase difference within the pole. Let us see now how the use of shaded poles actually produce a torque or turning force in a single-phase induction motor. The single-phase AC energizes the unshaded portions of the poles first and creates magnetic fields in these areas. The phase difference caused by the higher inductance of the shaded sections is responsible for the lag in the development of magnetic fields in them. As the current cycle changes, the same action will take place in all the poles. Relative motion, the basic requirement of an induction motor, has been satisfied. The rotor turns. Because of the relatively small phase difference developed by this method, shaded pole motors start slowly and are not used where a great deal of starting torque is required. There is another way to start the single-phase induction motor. In addition to the main poles, starting poles with separate windings are used. Phase difference is created by using high resistance wires for the starting poles and low resistance wires for the main poles. To understand the operation of the starter winding, it is necessary to bear in mind something of the character of the AC power supply. In any pure inductance, current lags behind voltage by 90 degrees. But since the heavy winding is not a pure inductance, but a large inductance, the current will lag the voltage in this winding by less than 90 degrees, say 80 degrees. The greater resistance of the starter winding, because of its smaller diameter, causes the current to lag the voltage by much less than 90 degrees, say 30 degrees. The net effect is then that the greater resistance of the starter windings causes the phase shift to be less than that of the main winding. We now have in effect a two-phase current. The phase difference causes the starter windings to be energized before the main windings. Magnetic fields are formed progressively. This is called a split-phase motor. The magnetic field now rotates electrically. The basic requirement of relative motion has been satisfied and the motor has been started. When the rotor has attained approximately 25% of its rated speed, a centrifugal switch opens and disconnects the starter windings. The phase shift accomplished by the addition of starter windings is not very great. The starting torque in this split-phase arrangement, although better than that in the shaded pole motor, is still not too good. A third method for starting single-phase induction motors is the use of starter windings with high-capacity electrolytic capacitors. We saw in our last example how a phase difference was developed by the use of starter windings. Now, when a capacitor is added in series with a starter winding, it offsets the inductance, causing an even greater phase shift between the two currents. This is a capacitor start motor with a centrifugal switch. When the motor has attained 25% of its running speed, the centrifugal switch disconnects the starter windings. The centrifugal switch is mounted on the rotor shaft and is the type used on most split-phase motors. Since the greatest phase shift and relative motion is caused by the capacitor start method, it is used in situations where good starting torque is an important consideration. Among the principal types of AC motors in use, the synchronous motor is used in situations where constant running speed is the governing factor. You'll remember that the operation of the induction motor depended on relative motion, that is, the difference in speed between the rotor and the rotating magnetic field. This relative motion induced an EMF in the rotor. In the synchronous motor, however, a different situation exists. Here, a multi-phase source of AC is applied to the stator windings, producing a rotating field, and a separate DC voltage is applied to the rotor windings, producing an independent magnetic field. There is no need for relative motion here. The synchronous motor is so designed that the rotor and the field rotate at the same speed. This is of importance when synchronous motors are used to drive equipment requiring this characteristic. Now to summarize, all rotating generators produce AC internally. The AC character of the output is maintained in the AC generator by the use of slip rings as load connectors. The frequency of the AC generator can be changed by introducing additional magnetic fields. The formula for frequency can be expressed as follows. F, or frequency in cycles per second, equals P, the number of poles, times N, revolutions per minute, over 120. The simplest AC generator shown here is the single-phase generator. This machine produces a single AC voltage. In the two-phase generator, we find two loops 90 degrees apart, and in the three-phase generator, three loops 120 degrees apart. The output of the three-phase generator, therefore, will be 3 AC voltages 120 degrees out of phase. The field of an AC generator is always excited by a DC voltage, in this case by a small DC generator in tandem. When it comes to AC motors, the most commonly used is the induction motor, whose basic operating principle is the electrical rotation of the magnetic field. Relative motion must be maintained. That is, the rotor must move at a slower pace than the rotating field. The three-phase induction motor is very efficient and widely used. The single-phase induction motor differs from the polyphase motors in that it is not self-starting. Since there is no phase difference in the single-phase current, the field pulsates instead of rotating. In order to create relative motion between field and rotor, shaded poles may be used. The unshaded portion is energized first. Because of the increased inductance in the shaded portion, the field here develops more slowly. Another method is the use of starter poles with high resistance windings. The high resistance in the starter winding causes the current to be out of phase with the current in the low resistance winding of the main pole. Magnetic fields are formed progressively and relative motion is begun. In the third method, a capacitor is placed in series with the starter winding. This causes a greater phase shift between the two windings. We now have two-phase operation on single-phase voltage. In synchronous motors, there is no need for relative motion. The EMF needed for the rotor is supplied from an outside DC source. Here, the rotor and the revolving field rotate at the same speed. AC rotating electrical equipment is the most practical for a multitude of uses. Knowledge of the principles of alternating current is essential to intelligent operation of such equipment.